We'll now look at an important example of a sequence. And let's ask the following question first. Is it possible to construct a sequence of all rational numbers listed in order of magnitude. And let me just modify it a little bit. All positive rational numbers. So clearly this is possible for natural numbers, right? So just because for natural numbers because I can set Sn equal to n, right? So then that way I'll list all natural numbers in order. So this sort of trivial sequence accomplishes a job. All right, but how about the sequence of all rationals, of all positive rationals? Well, let's suppose that the same thing can be done for rational. That is, I can set Sn, which lists all rational numbers in order, right? So that means that for any q in q plus set of all positive rationals, we have that Sn, let's say Sn0 is equal to q for some n0 natural number. So what I'm saying is that if I have a sequence of all rational numbers listed in order, then if I take any rational number, it must appear somewhere in my sequence, which means that there must be an instance of an index, which I denoted by n0, such that Sn0 is equal to that randomly chosen q that I took. And also, because these things are listed in order, so also, if q is q0 is greater than q1, right, then Sn0 is equal to Q0, Sn1 is equal to Q1, where N0 must be greater than N1, right? What does it mean to have the rationals listed in order? If I take two rationals, Q0 and Q1, they will both appear in my sequence, right? Because the sequence lists all possible rational numbers. So then Q0 is going to be some Sn0, Q1 is going to be some Sn1, and because the terms are listed in order, if Q0 is bigger than Q1, then Q0 must appear in my sequence later than Q1. So that means that its index, N0, index of Q0 equal to N0, should be greater than N1. Okay, so if that is possible, then Q0, or Q1 actually, is the, or should be, the smallest positive rational number. Right, again, because I listed things in order. Okay, but then if that is the case, then by denseness of Q, denseness of a set of all rational numbers, there exists, let's say, an S in Q such that S belongs to the interval from 0 to Q1. Right? And so that means that S is a rational number a positive rational number that is smaller than Q1. So therefore, S must be listed before Q1. So S must appear in Sn before S1. Before Q1, actually. And that is a contradiction. And so we conclude from this. So the conclusion, positive rational numbers cannot be listed as a sequence in order. Or in increasing order. Okay? So that's a conclusion that we're going to make here. And now I'm going to try the following construction. So next, I'm going to let the height of a rational number any rational number I can write as P over Q to be P plus Q when the number is written in an irreducible form. So for example, the height of 1/2 is going to be equal to 1 plus 2 equal to 3. Height of let's say 3/9 is the same thing as a height of 1/3, right? Because that would be an irreducible form of 3/9. 1 plus 3 equal to 4, etc. Okay, so what can I do with this notion? I'm going to try the following thing with it. So I'm going to construct the following table. In this table, I'm going to do the following. So the first column is going to be a height. By the way, from the way I introduced the height, it should be clear that so the height is you compute it from an irreducible form of a rational. A rational number is a ratio of two integers, and therefore the height is always going to be an integer, right? Because it's the sum of two integers. So I'm going to construct a table of positive heights. So what are the possible values of positive heights? So in the first column, I'm going to list the height. So it can be 1, 2, 3, 4, etc., right? So because height, in this case for positive heights are going to be natural numbers, then the first column is simply going to be a listing of all possible natural numbers. And as a second column, I'm going to list all rationals with a given height. Okay, so what would be possible rationals with a height 1? So that means that P plus Q, right, must be equal to 1. If I'm listing all rationals that are strictly bigger than 0, then the only possible choices for P and Q in this case are going to be 1 and 0. Either P is 1, Q is 0, or Q is 1 and P is 0. Obviously, denominator cannot be equal to 0. So that means that 1 over 0 is not a legitimate entry in this table. And the second entry is 0 over 1, if p is 0, q is 1. And I'm listing all positive rationals, so 0 is not a possible entry. So then nothing for 1. Now, what about 2? Again, 2 is, how do I get 2 as an addition of two positive integers? I can have 0 plus 2. I can have 1 plus 1, and I can have 2 plus 0. So q is not allowed to be 0, so that is out. 0 over 2, again, is not possible because 0 is not a positive rational. So then the only possible choice in this case is going to be p is 1 and q is 1. So p over q is 1. So 1 is the only possible entry corresponding to the height 2. How can I write phi? I can write phi as 0 plus phi, 2 plus 1, 1 plus 2, and 0 plus phi. Dividing by 0 is impossible. 0 is not a part of positive rationals. So I get only two choices here. P is 1, Q is 2, and P is 2, Q is 1. P is 1, Q is 2 is 1/2, and P is 2, Q is 1, that is 2, right? So only two entries here. What about 4? Again, 0 plus 4 is not going to work. 4 plus 0 is not going to work. So what we are allowed to have is 3 plus 1, 2 plus 2, and 1 plus 3. 2 plus 2 means that P and Q are both 2. 2 over 2 is not irreducible, so that is not going to appear in this line. So only 1 plus 3 and 3 plus 1 would work. So 1/3 and 3. And let's just do one more so that things are absolutely clear. How am I doing this? So what do we have for 5? 5 plus 0 is not going to work. 0 plus 5 is not going to work. 1 plus 4, so 1/4, is a legitimate entry. Then 2 plus 3, 2/3. 3 plus 2, 3/2. And 4 over 1, which is 4, right? So we have 4 possible heights here. So then the conclusions from this construction are going to be that, so we're going to note a couple of things here. Number one, every rational number has a height, and therefore every rational number will appear on some line in this table. And number two, there are always going to be at most finitely many numbers with a given height, right? Because, for example, if height is n, I cannot have more than n plus 1 numbers with that height. So there are finitely many rationals, positive rationals, with a given height. Okay, so then I'm going to make the following identification. So now looking at the right side of my table, one I'm going to call S1, 1/2 will be S2, 2 will be S3, 1/3 is S4, 3 I'm going to call S5, then 1/4 is S6, 2/3 S7, S8, 4 is S9, and I can continue like that forever, right? The way I'm going to label S's is I'm going to move down along the different heights, and in each line corresponding to a given height, I have finitely many rationals so that I can continue labeling things like this. So in this case, in this way, actually, I will be able to construct a sequence that lists all positive rationals. Right? Because in this way, I should be able to enumerate all possible rational numbers. If I have a given rational number, that rational number, if you pick any rational number you want, that rational number is going to have a height. Because it has a height, it will appear at some line in this table. So that means that by following this enumeration procedure that I am showing to you on the screen, eventually I'll reach that number, that my randomly chosen rational number, and that rational number then will have some index. One thing that you can immediately see is that here S1 is equal to 1, S2 is 1/2, S3 is 2. So you start at 1, then you go down, then you go up, then you go down, then you go up. You go down, you go up, further up, further up. So the rational numbers in this case, they appear in a sequence, but they're not listed in order. So that is a necessary thing here, because we just proved that if I want to construct a sequence of all rational numbers, those rational numbers cannot be listed in order. But apparently you can construct a sequence of all rationals, of all positive rationals, where these numbers are not listed in order. So that's what we accomplished here. So, important thing to remember here as again related to our proof that rationals in the sequence are not in an increasing order. Okay. All right. So finally, for this example, so next, I'm going to let T be any positive real number. Okay? Question. How many rational numbers are there in the interval t minus epsilon t plus epsilon for any epsilon greater than 0. And you remember that before, it might have been actually a question on the test, we concluded that by denseness of Q, there are infinite many rationals like that. And if you remember, the way we showed it was that we assumed that there are finitely many rationals of this sort, and then you are able to use the denseness of Q to find another rational between the largest of these numbers that you found and t plus epsilon. Okay, what does that mean? So therefore, for any epsilon greater than 0, there are infinitely many terms of the sequence Sn of all positive rationals inside the interval t minus epsilon t plus epsilon. And what does it imply? The theorem that we proved last time. So therefore, by a theorem from last time, if the interval t minus epsilon to t plus epsilon contains infinitely many terms of my sequence inside any interval t minus epsilon t plus epsilon, so for any epsilon if this is true, then there exists a subsequence S and K such that the limit K goes to infinity of S and K is equal to 1. So that means that Sn has actually a spectacular property. It means that the sequence Sn of all rationals contains subsequences that converge to any real number any positive real number that you can think of. So once again, let's just think about it. I pick any real number greater than 0. This tells me that the sequence of all rational numbers should contain a subsequence which converges to that arbitrarily chosen real number. Which means that the sequence of all rationals actually, it has to be pretty wild, right? Because I can pick terms. So for example, if you look at a sequence -1 to the power n, right? You know that from that sequence I can extract subsequences convergent to 1 and -1, right? Because the sequence oscillates between 1 and -1. So I should be able to pick the sequences, subsequences like that. In this case, from a sequence of all rationals, I should be able to extract subsequences that converge to any number, any positive real number, which seems to indicate that the sequence of all rationals must oscillate really wildly. In fact, oscillate between 0 and plus infinity, because if I want to be able to choose a subsequence which converges, for example, to 1000, that means that my sequence should continue oscillating in such a way that it has terms that are close to 1000 as n goes to infinity, right? Because otherwise, if the window of oscillations, for example, is from 0 to 100, I should not be able to find a subsequence which goes to 1000. And because there are subsequences which converge to any positive real number, that means that the oscillations actually are going between 0 and plus infinity. And this actually corresponds to what we said in this comment here, is that the rationals in this sequence, it's very important that the rationals in this sequence are not listed in order. So that means that you should see wild oscillations, and you do, in fact. All right, so in the next lecture, then we're going to return to some theoretical questions, and eventually I will go back to example of the sequence of all rationals to illustrate some points of a theory that we're just going to discover soon.